find a compatible 20 amp single pole breaker for the Wh B20 4040CT panel, the Bryant website indicates the Bryant BR2020 is a direct replacement. If the Bryant BR2020 breaker is not available, consider alternative options from other reputable manufacturers. These alternatives include the Square DQ OP2020, the GETHQ L220, the Eaton BR2020, and the Siemens Q220. When selecting a replacement breaker, it is important to ensure that it has the same amperage and voltage rating as the original breaker. Always refer to the manufacturer's instructions for proper installation and safety precautions. If there is any uncertainty about which breaker to use, consult with a qualified electrician. Breakers protect electrical circuits from damage caused by overcurrent or short circuits. They are an essential safety component in any electrical system. A circuit breaker is an automatically operated electrical switch designed to protect an electrical circuit from damage caused by excess current from an overload or short circuit. Its basic function is to interrupt current flow after a fault is detected. Unlike a fuse, which is a one-time use device, a circuit breaker can be reset either manually or automatically to resume normal operation. Circuit breakers are made in varying sizes, from small devices that protect individual household appliances up to large switchgear designed to protect high-voltage circuits feeding an entire city. The increasing demands for electricity and the aging of existing electrical infrastructure necessitate a closer look at circuit breaker technology, its types, operation, and maintenance. Circuit breakers can be classified based on their operating voltage, interrupting rating, construction type, and tripping characteristics. Low-voltage circuit breakers are typically used in residential, commercial, and industrial applications for circuits rated up to 600 volts. Medium-voltage circuit breakers are used in distribution systems and industrial applications for circuits rated from 600 volts to 69 kilovolts. High-voltage circuit breakers are used in transmission systems for circuits rated above 69 kilovolts. Another classification is based on the interrupting rating, which is the maximum fault current that the breaker can safely interrupt. Breakers are rated in kiloamps, and it's crucial to select a breaker with an interrupting rating sufficient for the potential fault current at its installation location. The interrupting rating should be higher than the available fault current. Various construction types of circuit breakers exist, including air circuit breakers, oil circuit breakers, vacuum circuit breakers, and sulfur hexafluoride circuit breakers. Air circuit breakers use air at atmospheric pressure to extinguish the arc. Oil circuit breakers use oil to insulate and extinguish the arc. Vacuum circuit breakers use a vacuum to extinguish the arc. Sulfur hexafluoride circuit breakers use sulfur hexafluoride gas to extinguish the arc. Each type has its advantages and disadvantages in terms of cost, maintenance, and performance. Tripping characteristics define how quickly a circuit breaker will trip under different overcurrent conditions. These characteristics are typically represented by time current curves, which plot the tripping time against the overcurrent level. Different types of tripping characteristics are available to suit various application needs, such as inverse time, definite time, and instantaneous trip. Circuit breakers operate on the principles of thermal or magnetic sensing, or a combination of both. Thermal circuit breakers use a bar-metallic strip that bends when heated by the overcurrent. The bending of the strip trips the breaker mechanism, opening the circuit. Magnetic circuit breakers use an electromagnet that trips the breaker mechanism when the current exceeds a certain level. Some breakers use a combination of thermal and magnetic sensing to provide both overload and short circuit protection. Regular maintenance is essential to ensure the reliable operation of circuit breakers. Maintenance tasks include visual inspection, cleaning, lubrication, and testing. Visual inspection involves checking for any signs of damage, such as cracks, corrosion, or overheating. Cleaning removes dust and debris that can interfere with the breaker's operation. Lubrication ensures that the moving parts operate smoothly. Testing verifies that the breaker trips correctly under overcurrent conditions. Several factors influence the selection of a circuit breaker for a specific application. These factors include the voltage rating, current rating, interrupting rating, tripping characteristics, and environmental conditions. The voltage rating must be equal to or greater than the circuit voltage. The current rating must be equal to or greater than the maximum continuous current in the circuit. The interrupting rating must be greater than the available fault current. The tripping characteristics must be appropriate for the type of load being protected. The environmental conditions, such as temperature and humidity, must be within the breaker's operating limit. Circuit breakers play a crucial role in electrical safety and system reliability. Understanding their types, operation, maintenance, and selection criteria is essential for electrical engineers, technicians, and anyone involved in the design, installation, and maintenance of electrical systems. As technology advances, circuit breakers are becoming more sophisticated, with features such as remote monitoring, communication capabilities, and advanced protection functions. These advancements enhance the safety, reliability, and efficiency of electrical systems. The selection of an appropriate circuit breaker involves careful consideration of various factors to ensure that it can adequately protect the electrical circuit and equipment it serves. Firstly, determine the voltage rating. The voltage rating of the circuit breaker must be equal to or greater than the maximum voltage of the electrical circuit it will protect. Using a circuit breaker with a lower voltage rating can lead to insulation breakdown and potential hazards. Secondly, identify the current rating. The current rating, also known as the ampacity of the circuit breaker, should be matched to the circuit's load requirements. It is generally recommended to choose a circuit breaker with a current rating that is approximately 125% of the continuous load current. This provides a safety margin to prevent nuisance tripping due to normal load fluctuations. Thirdly, verify the interrupting capacity. The interrupting capacity, also referred to as the short circuit current rating, indicates the maximum fault current that the circuit breaker can safely interrupt without sustaining damage. It is crucial to select a circuit breaker with an interrupting capacity that exceeds the available fault current at the installation location. Fault current calculations should be performed to determine the maximum potential fault current. Fourthly, assess the tripping characteristics. Circuit breakers are designed with different tripping characteristics to provide protection against various types of overcurrent conditions, such as overloads and short circuits. Common tripping characteristics include inverse time, definite time, and instantaneous trip. Inverse time circuit breakers have a tripping time that is inversely proportional to the overcurrent level. Definite time circuit breakers trip after a specific time delay, regardless of the overcurrent level. Instantaneous trip circuit breakers trip almost immediately when a short circuit occurs. Fifthly, account for the ambient temperature. The ambient temperature can affect the performance of circuit breakers. Higher temperatures can reduce the current carrying capacity of the breaker, while lower temperatures can increase the tripping time. It is important to select a circuit breaker that is suitable for the expected ambient temperature conditions. Correction factors may need to be applied to the current rating to account for temperature variations. Sixthly, evaluate the environmental conditions. The environmental conditions at the installation location can also impact the selection of a circuit breaker. Factors such as humidity, dust, and corrosive substances affect the breaker's performance and longevity. Circuit breakers are available with different environmental protection ratings, such as NEMA or IP ratings, to indicate their suitability for various environments. Seventhly, consider the physical size and mounting requirements. The physical size and mounting requirements of the circuit breaker should be compatible with the electrical panel or enclosure where it will be installed. Ensure that there is sufficient space for the breaker and that it can be securely mounted. Eighthly, check the agency listings and certifications. Circuit breakers should be listed and certified by recognized testing laboratories such as UL or CSA. These listings indicate that the breaker has been tested and meets applicable safety standards. Ninthly, factor in the application-specific requirements. Depending on the specific application, there may be additional requirements to consider when selecting a circuit breaker. For example, in critical applications such as hospitals or data centers, it may be necessary to use circuit breakers with enhanced reliability and monitoring capabilities. Tenthly, consult with a qualified electrician. If there is any uncertainty about which circuit breaker to select, it is always best to consult with a qualified electrician. An electrician can assess the specific requirements of the electrical circuit and recommend the appropriate circuit breaker. When installing a circuit breaker, safety precautions are paramount to prevent electrical shock and ensure proper operation. Firstly, always de-energize the circuit. Before working on any electrical circuit, always turn off the power at the main breaker or disconnect switch. Use a voltage tester to verify that the circuit is de-energized. Secondly, wear appropriate personal protective equipment. Wear safety glasses and insulated gloves to protect yourself from electrical hazards. Avoid wearing loose clothing or jewelry that could come into contact with energized parts. Thirdly, use insulated tools. Use only insulated tools that are specifically designed for electrical work. These tools provide an extra layer of protection against electric shock. Fourthly, follow the manufacturer's instructions. Always follow the manufacturer's instructions for installing the circuit breaker. Incorrect installation can lead to malfunction or safety hazards. Fifthly, ensure proper grounding. Make sure that the electrical panel and circuit are properly grounded. Grounding provides a path for fault current to flow back to the source, tripping the breaker and preventing electrical shock. Sixthly, tighten connections securely. Tighten all connections securely to prevent loose connections, which can cause overheating and arcing. Use a torque wrench to tighten connections to the specified torque value. Seventhly, label the circuit breaker. Label the circuit breaker clearly to indicate the circuit it protects. This makes it easier to identify and troubleshoot circuits in the future. Eighthly, test the circuit breaker. After installing the circuit breaker, test it to ensure that it is working properly. Use a circuit breaker tester to verify that it trips under overload and short circuit conditions. Ninthly, inspect for damage. Before installing a circuit breaker, inspect it for any signs of damage, such as cracks, corrosion, or overheating. Do not install a damaged circuit breaker. Tenthly, seek professional help if needed. If you are not comfortable working with electricity, or if you have any questions or concerns, seek professional help from a qualified electrician. Electrical work can be dangerous, and it is always best to err on the side of safety. When dealing with electrical panels and circuit breakers, it is essential to understand the relevant electrical codes and regulations to ensure compliance and safety. These codes and regulations provide guidelines for the design, installation, and maintenance of electrical systems, including the selection and installation of circuit breakers. Firstly, familiarize yourself with the National Electrical Code. The National Electrical Code, or NEC, is a widely adopted set of standards for electrical installations in the United States. It provides comprehensive requirements for electrical wiring equipment and systems, including circuit breakers. Secondly, understand the local electrical codes. In addition to the NEC, many local jurisdictions have their own electrical codes that may be more stringent or have specific requirements for certain types of installations. It is important to be aware of and comply with all applicable local electrical codes. Thirdly, adhere to the NEC requirements for circuit breaker selection. The NEC provides specific requirements for selecting circuit breakers based on the type of circuit, the load requirements, and the available fault current. These requirements are intended to ensure that circuit breakers provide adequate protection against overcurrent and short circuit conditions. Fourthly, follow the NEC requirements for circuit breaker installation. The NEC also provides detailed requirements for installing circuit breakers, including proper mounting, wiring, and grounding. These requirements are intended to ensure that circuit breakers are installed safely and correctly. Fifthly, comply with the NEC requirements for circuit breaker labeling. The NEC requires that circuit breakers be clearly labeled to indicate the circuit they protect. This makes it easier to identify and troubleshoot circuits in the future. Sixthly, adhere to the NEC requirements for circuit breaker maintenance. The NEC provides guidelines for maintaining circuit breakers, including regular inspection and testing. These guidelines are intended to ensure that circuit breakers continue to operate properly over time. Seventhly, be aware of the NEC requirements for arc fault circuit interrupters. Arc fault circuit interrupters, or SIs, are special types of circuit breakers that are designed to protect against arc faults, which can cause fires. The NEC requires SIs in certain types of circuits, such as those that serve bedrooms and other living areas. Eighthly, understand the NEC requirements for ground fault circuit interrupters. Ground fault circuit interrupters, or GFCIs, are special types of circuit breakers that are designed to protect against ground faults, which can cause electrical shock. The NEC requires GFCIs in certain locations, such as bathrooms, kitchens, and outdoor areas. Ninthly, comply with the NEC requirements for overcurrent protection. The NEC requires that all electrical circuits be protected against overcurrent by either circuit breakers or fuses. The overcurrent protection device must be sized appropriately for the circuit and the load it serves. Tenthly, consult with a qualified electrician. If you have any questions or concerns about electrical codes or regulations, consult with a qualified electrician. An electrician can help you understand the requirements and ensure that your electrical system is compliant and safe. There are several common problems that can occur with circuit breakers, leading to nuisance tripping, failure to trip, or other malfunctions. Understanding these problems and how to troubleshoot them can help you maintain a safe and reliable electrical system. Firstly, nuisance tripping. Nuisance tripping occurs when a circuit breaker trips for no apparent reason, even though there is no overload or short circuit. This can be caused by several factors, such as loose connections, faulty wiring, or excessive load fluctuations. Secondly, failure to trip. Failure to trip occurs when a circuit breaker fails to trip in response to an overload or short circuit. This can be caused by a faulty breaker mechanism, corrosion, or damage to the breaker. Thirdly, overheating. Overheating can occur when a circuit breaker is overloaded or when there are loose connections. Overheating can damage the breaker and create a fire hazard. Fourthly, corrosion. Corrosion can occur when circuit breakers are exposed to moisture or corrosive substances. Corrosion can damage the breaker and cause it to malfunction. Fifthly, damage. Circuit breakers can be damaged by physical impact, electrical surges, or other factors. Damage can affect the breaker's performance and safety. Sixthly, loose connections. Loose connections can cause overheating, arcing, and nuisance tripping. It is important to tighten all connections securely to prevent these problems. Seventhly, faulty wiring. Faulty wiring can cause overloads, short circuits, and nuisance tripping. It is important to inspect wiring regularly and repair any problems. Eighthly, excessive load fluctuations. Excessive load fluctuations can cause nuisance tripping. This can be caused by appliances that draw a lot of power intermittently, such as refrigerators or air conditioners. Ninthly, improper breaker size. Using the wrong size circuit breaker can lead to overloads, overheating, and nuisance tripping. It is important to use the correct size breaker for the circuit and the load it serves. Tenthly, old or worn-out breakers. Circuit breakers can wear out over time, especially if they are frequently tripped. Old or worn-out breakers may not trip reliably and should be replaced. To troubleshoot circuit breaker problems, firstly, check for loose connections. Use a screwdriver to tighten all connections on the circuit breaker and in the electrical panel. Secondly, inspect the wiring. Look for any signs of damage, such as frayed insulation or exposed wires. Repair any damaged wiring. Thirdly, reduce the load. If the circuit breaker is tripping frequently, try reducing the load on the circuit. Disconnect some appliances or move them to a different circuit. Fourthly, replace the circuit breaker. If the circuit breaker is old or worn out, or if it is damaged, replace it with a new one of the correct size and type. Fifthly, consult with a qualified electrician. If you are not comfortable troubleshooting circuit breaker problems yourself, consult with a qualified electrician. An electrician can diagnose the problem and recommend the appropriate solution. Arc fault circuit interrupters and ground fault circuit interrupters are specialized types of circuit breakers that provide enhanced protection against electrical hazards. Understanding the differences between these devices and their applications is essential for ensuring electrical safety. Firstly, arc fault circuit interrupters. Arc fault circuit interrupters, or SIs, are designed to protect against arc faults, which are dangerous electrical discharges that can cause fires. Arc faults can occur when damaged or deteriorated wiring creates a path for current to flow through the air, generating heat and potentially igniting nearby materials. Secondly, ground fault circuit interrupters. Ground fault circuit interrupters, or GFCIs, are designed to protect against ground faults, which occur when current leaks from an electrical circuit to ground. Ground faults can cause electrical shock if a person comes into contact with the energized surface and a grounded object. Thirdly, the difference. The main difference between SIs and GFCIs is the type of electrical hazard they protect against. SIs protect against arc faults, which can cause fires, while GFCIs protect against ground faults, which can cause electrical shock. Fourthly, SI applications. SIs are typically installed in circuits that serve bedrooms, living rooms, and other areas where arc faults are more likely to occur. The NEC requires SIs in most new residential construction. Fifthly, GFCI applications. GFCIs are typically installed in locations where there is a high risk of electrical shock, such as bathrooms, kitchens, outdoor areas, and near swimming pools. The NEC requires GFCIs in these locations. Sixthly, how SIs work. SIs work by detecting the unique characteristics of arc faults, such as irregular current flow and high-frequency noise. When an arc fault is detected, the SI trips the circuit breaker, interrupting the flow of current and preventing a fire. Seventhly, how GFCIs work. GFCIs work by monitoring the current flowing through the hot and neutral wires of a circuit. If there is a difference in current between the two wires, it indicates that current is leaking to ground. When a ground fault is detected, the GFCI trips the circuit breaker, interrupting the flow of current and preventing electrical shock. Eighthly, testing of SIs and GFCIs. It is important to test SIs and GFCIs regularly to ensure that they are working properly. Most SIs and GFCIs have a test button that can be used to simulate a fault condition. When the test button is pressed, the device should trip the circuit breaker. Ninthly, replacing SIs and GFCIs. SIs and GFCIs can wear out over time and should be replaced periodically. The manufacturer's instructions will provide guidance on when to replace the device. 10thly, consulting with a qualified electrician. If you have any questions about SIs or GFCIs, or if you need help installing or testing them, consult with a qualified electrician. An electrician can ensure that the devices are installed correctly and are providing adequate protection. Electrical panels and circuit breakers are essential components of any electrical system, providing a central point for distributing power and protecting circuits from overloads and short circuits. Understanding the basics of electrical panels and circuit breakers is crucial for maintaining a safe and reliable electrical system. Firstly, electrical panels. Electrical panels, also known as breaker boxes or load centers, are metal enclosures that house circuit breakers. They serve as the main distribution point for electricity in a building. Secondly, circuit breakers. Circuit breakers are automatic switches that protect electrical circuits from damage caused by overcurrent or short circuits. They are designed to trip and interrupt the flow of electricity when a fault is detected. Thirdly, panel components. Electrical panels typically include a main breaker, which controls the power to the entire panel, and several branch circuit breakers, which control the power to individual circuits. Fourthly, breaker types. There are several types of circuit breakers, including standard breakers, which provide basic overcurrent protection, ground fault circuit interrupters, which protect against ground faults, and arc fault circuit interrupters, which protect against arc faults. Fifthly, panel sizing. Electrical panels are sized based on the amperage of the main breaker and the number of circuit breakers they can accommodate. The size of the panel should be adequate for the electrical load of the building. Sixthly, breaker sizing. Circuit breakers are sized based on the amperage of the circuit they protect. The breaker should be sized to match the ampacity of the wiring and the load it serves. Seventhly, panel labeling. Electrical panels should be clearly labeled to indicate the circuits that each breaker controls. This makes it easier to identify and troubleshoot circuits. Eighthly, panel maintenance. Electrical panels should be inspected regularly for signs of damage, such as corrosion, overheating, or loose connections. Any problems should be corrected promptly. Ninthly, breaker testing. Circuit breakers should be tested periodically to ensure that they are working properly. Most breakers have a test button that can be used to simulate a fault condition. Tenthly, safety precautions. When working with electrical panels and circuit breakers, always take safety precautions such as turning off the power, wearing insulated gloves, and using insulated tools. Electrical work can be dangerous, and it is always best to err on the side of safety. When selecting a circuit breaker, it is crucial to consider the specific requirements of the electrical circuit and the equipment it will protect. Choosing the right circuit breaker ensures proper protection against overloads and short circuits, preventing damage to equipment and reducing the risk of electrical fires. Firstly, determine the circuit voltage. The voltage rating of the circuit breaker must be equal to or greater than the voltage of the electrical circuit it will protect. Common voltage ratings for residential circuits include 120 volts and 240 volts. Secondly, calculate the circuit current. The current rating of the circuit breaker should be matched to the circuit's load requirements. To calculate the circuit current, add up the amperage of all the devices and appliances that will be connected to the circuit. Thirdly, select the appropriate breaker size. The circuit breaker should be sized to protect the wiring from overheating. The National Electrical Code provides guidelines for selecting the appropriate breaker size based on the wire gauge and the circuit current. Fourthly, consider the interrupting capacity. The interrupting capacity of the circuit breaker should be greater than the available fault current at the installation location. The available fault current can be calculated using engineering methods or obtained from the utility company. Fifthly, choose the correct breaker type. There are several types of circuit breakers available, each designed for specific applications. Standard breakers provide basic overcurrent protection. Ground fault circuit interrupters protect against ground faults. Arc fault circuit interrupters protect against arc faults. Sixthly, account for ambient temperature. The ambient temperature can affect the performance of circuit breakers. Higher temperatures can reduce the current carrying capacity of the breaker, while lower temperatures can increase the tripping time. Seventhly, evaluate environmental conditions. The environmental conditions at the installation location can also impact the selection of a circuit breaker. Factors such as humidity, dust, and corrosive substances can affect the breaker's performance and longevity. Eighthly, check agency listings and certifications. Circuit breakers should be listed and certified by recognized testing laboratories such as UL or CSA. These listings indicate that the breaker has been tested and meets applicable safety standards. Ninthly, factor in application-specific requirements. Depending on the specific application, there may be additional requirements to consider when selecting a circuit breaker. For example, in critical applications, it may be necessary to use circuit breakers with enhanced reliability and monitoring capabilities. Tenthly, consult a qualified electrician. If you are unsure about which circuit breaker to select, consult a qualified electrician. An electrician can assess the specific requirements of the electrical circuit and recommend the appropriate circuit breaker.